Okay, so welcome to the colloquium of Instituto Balseiro, and today I'm really pleased to introduce Professor Mark Srednicki. He's a professor of physics at the University of Santa Barbara. He has made really fundamental contributions to quantum field theory, statistical mechanics, gravity, quantum many-body physics, and in particular, we all know him very well for his work on entanglement entropy and also eigenstate thermalization hypothesis, which we'll hear more about today. But I thought I would also make maybe a more personal introduction of him. Often when we look back, we remember when we were students, particularly in our PhD, maybe for months, struggling to understand complicated things. And when we recall those times, we usually are able to identify, some intellectual heroes. And by that, we mean, people that have made really important contributions, but besides, they were able to, explain things to us in a way we could understand, and often also, change the way we think. And so in that sense, I think, Mark Srednicki is one of our heroes in quantum field theory. So I think that's, really important. So we are super happy to have him. He's visiting for 10 days. In fact, he's lecturing in the quantum field theory school that maybe you have seen around. There are more than 80 people participating in that school. And I also want to take this opportunity to thank the Maldacena program for invited professors that has made possible his visit today. And so before we begin, just one announcement. In case you want to continue, discussing or the conversation afterwards, we'll have some refreshments and coffee. That's going to happen in Ex Biblioteca, so next to the Lopez Dávalos cafeteria. So if you want to continue discussing after the colloquium, there will be time. Just go there and we can meet and continue. Okay, so with that, let me introduce then Mark Srednicki to his talk about quantum chaos and the foundations of statistical mechanics. Thanks.
Thank you very much for that very kind introduction. I have to tell you, though, I am not as smart as you think I am. And I can prove it. I can prove it because this is my first time in Argentina. And having been here for a week, I realized that it was a terrible mistake not to come sooner. So I've had a wonderful time here. Thanks very much to Gonzalo and to the other organizers of the school. It's been fantastic. And today I'm going to tell you a story that starts 30 years ago. At the time I was mostly working on particle astrophysics, properties of dark matter, and things like that. And then the teaching assignments for the next year came out, and I had been assigned to teach statistical mechanics, which I had never taught before. And apparently the usual people who would usually teach it were unavailable for whatever reason, and so they asked me, and I said, fine, I'll be happy to do that. So then I started thinking about statistical mechanics and some of the classic problems of statistical mechanics. And in particular, coming out of quantum mechanics, all my research work involved quantum mechanics in some form or another. I started thinking about, I imagine I have a system, and I will just go to the next slide here, like a box of gas, and I want to treat it quantum mechanically, and I want to think about it as being completely isolated from the environment, and I'm going to have some, wrong button, some atoms of the gas, which I'm going to think of just as little hard spheres, just to have a specific model. And I'm going to put them all in some corner of the box moving up. And then I want to see what happens. Of course, we all know what happens. If you wait a little bit, they'll bounce off each other, and they will eventually, pretty quickly, distribute themselves more or less uniformly in the box, and they'll have a Boltzmann distribution of momenta. And my idea for organizing the class was to start out by saying, how would we figure this out if we didn't know statistical mechanics, and explain that that was complicated, and then say, yes, but if we just use the principles of statistical mechanics, we can get the answer right away. But then I started wondering, well, how actually do you show this if you don't know statistical mechanics? Now, if we used classical mechanics for the box and the atoms in the box, then I had some idea of how this was supposed to work. I mean, if they're not perfectly aligned, then they bounce into each other and they knock each other around, and eventually they have more or less random-looking distribution of momenta, and they fill the box. And I knew there were words I had heard like ergodicity and chaos. I wasn't completely sure what those things were, but I thought, well, if I knew what those things were, then I could understand the classical part. But again, I'm a quantum physicist, not a classical physicist, so I wanted to do this with quantum mechanics. So I wanted to think of some initial wave function for these atoms, like put each one in a little Gaussian wave packet, and then start time evolving with the Schrodinger equation. And if the wave packets are small enough in both position and momentum space, then we know that the quantum mechanics is going to sort of mimic the classical mechanics for a while, and they'll be knocking each other around, and then we could rely on the classical description. But I didn't really want to do that. I wanted something really intrinsically quantum mechanical. I want to just start off with this initial state or something like this initial state. And then I wanted to just time evolve it with the Schrodinger equation and see that 5 minutes later it looked like this. But as I thought about this, I realized that I did not know how to do that. I had no idea. So then I was thinking, well, I must have skipped class the day this was explained. So I went to the library. I got out statistical mechanics books. I looked through them. And they all said stuff about this. I don't think any two of them said exactly the same thing. But they all said stuff. And the stuff that was in the books, I did not find convincing. I did not feel that I had gotten a solid understanding of this. And I became annoyed by this. So annoyed that I really wanted to figure it out. I really wanted to find an explanation that, for me, was better than what I could find in the books. But how am I going to do this? Well, as I said earlier, I had this idea that classical chaos had something to do with classical statistical mechanics. And I'd vaguely heard of something called quantum chaos. So I thought, maybe those people know something. So I started reading the quantum chaos literature. And I discovered two things. One, it was really interesting. They were doing a lot of really interesting things that I didn't know about before reading about it. And two, some of the things they knew indeed could be reinterpreted to give what I feel is a better story about how this happens in quantum mechanics. So that's what I'm going to tell you about. Okay. So we're going to make some basic assumptions. First of all, I'm going to assume I have many degrees of freedom. So like a box of gas with many atoms in it. But I also want to think at this point a little more generally. So we could maybe have a system of quantum spins or equivalently qubits that are coupled together on some sort of lattice. Lots of models like that are studied in condensed matter physics. But I want a lot of degrees of freedom. And then I want to say that there are some quantities we can observe, which I'm just going to call A, with an index I, because maybe we'll have more than one of them. And so for the gas, something we could imagine observing is a number operator. This is a quantum mechanical number operator with a subscript that says we're looking at a particular momentum. So this operator just counts how many particles have that momentum. So that's the kind of thing I want. It depends on the system, of course. If it's a spin system, these could be all the individual spins. But I want these things to be something you could imagine actually measuring. So connected to the physics of the system in some reasonable way. And also, it's not a complete set of observables, right? There are, in particular, we could consider multi-particle observables where I ask for the number of particles in this mode times the number in that mode, things like that. I don't want any of my observables to involve more than a few of the degrees of freedom. And again, this is because that's what we can do in the lab, right? If you are an experimental graduate student and I tell you to please go measure the 27-point correlation function of some variable, you're not going to be able to do it. Okay, and then I want to assume that we have some pure quantum state in whatever description is appropriate to the system, and that it is going to time evolve unitarily by the Schrodinger equation. We could also consider mixed states, but the sort of puzzles that arise in thinking about this are strongest for pure states, so I will only talk about pure states. And then I'm going to assume that the quantities of interest are the instantaneous expectation values of each of our set of observables. Now, in fact, we do not typically measure expectation values. We measure eigenvalues. But I want to assume that these numbers as functions of time suitably capture what's going on with the physics. And so if you were interested in fluctuations about this average for some particular A, I will allow you to put A squared on the list, and then the expectation value of A squared will give you the fluctuations of A, and you can put all the powers on the list if you want. So I am assuming that these quantities sufficiently capture the physics of what's going on. Okay. All right. So this system will have some expectation value of the Hamiltonian, which will be the total energy. This is, of course, time independent. Doesn't matter what time you take this expectation value. And I want to assume that the total energy is extensive. It's proportional to the number of degrees of freedom. So I have a finite amount of energy per degree of freedom. In statistical mechanical or thermodynamic language, that means the system is effectively at a finite temperature. There's some finite amount of energy per degree of freedom. And not, in quantum terms, it means we are not close to the ground state. We are well above the ground state. In general, there will be some quantum uncertainty. Unless this psi happens to be an exact energy eigenstate, there's quantum uncertainty in the energy given by the usual formula. And I want to assume that this is subextensive, that it scales as a power of n that's definitely less than 1, and I would actually like to make it no bigger than 1/2, although that's a relatively minor technical point. If you really want it to be 3/4 or something, I will let you do that. And the reason is we want delta E, the uncertainty in the energy, to be small compared to the total energy, because we want to think of our system as having some relatively definite total energy. When we do thermodynamics, we don't worry about the quantum uncertainty in the energy. And we are allowed not to worry about it because in the cases where we want to apply thermodynamics, that uncertainty is typically small. In fact, if you used for the quantum state not a pure state, but a thermal mixed state, a density matrix that's e to the minus beta h, for those of you who remember that, your statistical mechanics class, that will give you a quantum uncertainty with gamma of a half. And this just, when gamma is a half, it effectively means that there's an uncertainty in the energy of each degree of freedom of order 1. So that's quite uncertain. But the total, just by Poisson statistics, basically, you get a factor of the square root. So setting gamma, having gamma be no bigger than a half is completely consistent with what we usually do, the usual sorts of states we expect in a thermal system. Okay, and then, so to compare with things we do in standard stat mech, I want to define a thermal expectation value with this somewhat odd notation because I've already used angle brackets for quantum expectation values. And this will be just what you are taught to do in the so-called canonical ensemble in your statistical mechanics class. You take trace of the observable times e to the minus beta h, and you normalize. And in order to compute this thermal average, I need to know what beta is. Beta is physically the inverse temperature, and it will be fixed by having the correct relation to the energy. The energy of the system in statistical mechanics is the thermal average of the Hamiltonian itself, and I want to adjust beta so that when I take this thermal average, I get the energy that I actually get from the actual quantum state. Okay. So I don't want to say that the quantum state is the thermal density matrix. I just want to use that as a comparison to what we're going to get from the actual quantum state. Oh, and feel free to interrupt with questions, by the way. Okay, and I want to point out that these two statements, that the energy is extensive and the quantum uncertainty is subextensive, these are some restrictions on the sorts of initial states I'm going to allow. They're pretty mild restrictions, right? I haven't really done very much, but I am restricting the state somewhat. I want it to have an energy that's well above the ground state, and I want the quantum uncertainty in the total energy to be small compared to the total energy. Okay. I need a definition of thermal equilibrium, because one thing I learned very quickly when I started working on these ideas and talking to other people about them is that we would often have conversations where we eventually figured out we were talking past each other because we were using different definitions of what thermal equilibrium is. So I'm going to give you mine. If you have a different one, it's fine, but if we talk later, tell me what it is so that we don't talk past each other. Okay, mine is, and this is intended to sort of mimic what we would actually do in a lab if somebody handed us a box of gas and said, tell me if this box of gas is in thermal equilibrium. I have my list of observables that are the things I can imagine measuring. And I will say that the system is in thermal equilibrium at a particular time t if the quantum expectation value of each of my observables at that time is equal to the thermal expectation value within some tolerance. I can't demand perfect equality, and you wouldn't get perfect equality in a lab. So we have some tolerance, which would be set by experimental procedures. And so physically I'm imagining I have a box of gas, and I've handed it to a graduate student and said, here, tell me if this gas is in thermal equilibrium. What is the poor graduate student going to do? Well, can stick some thermometers in it in various places. And if the thermometers all read the same temperature, we'll probably say, yeah, it's in thermal equilibrium. Okay. No one in the history of humanity has ever done better than that. Okay. We have never determined the complete quantum state of anything. We determine a few things, and we go, yeah, thermal equilibrium. Okay. So that's important, right? Because if you do mathematical physics, there's a great temptation to be overly precise and overly mathematical, and then you come up with definitions that are too sharp and too restrictive so that they no longer actually conform to what people do in the real world. Okay, so I want to try to stick to some math that's close enough. Okay. Also notice this is time dependent. It could be true for a long time and then not be true. Maybe all the air in the room will spontaneously move to that corner and we'll be very unhappy. And we might also say, I don't think it's in thermal equilibrium anymore. Okay. Okay, I think I'm done with this slide. All right, so let's go back to thinking about some particular observable. And, for example, the number of particles with some particular momentum in a box of gas. And I want to, as in that cartoon of the atoms in the corner moving up, I want to imagine that this is a mode that's heavily occupied at time 0. And so it's much larger than the thermal expectation value. But then what do we expect to happen if we follow this expectation value in time? We expect it to relax to a thermal equilibrium value, maybe with some fluctuations. This is pure artist conception, by the way. This is not a calculation of anything. I've drawn a sort of zigzaggy line here to indicate there are fluctuations. And then, there'll continue to be some fluctuations. But what we expect to happen is that this will move to the thermal equilibrium value. That's the atoms knocking each other around and taking on a thermal distribution. And then it's going to stay here most of the time. And there'll be small fluctuations and rarely a big fluctuation when all the atoms go back into the corner, but we don't expect those to happen very often. Okay. And we all expect this to happen because we all did take the class in StatMech, or we all just live in the real world where we know that this is what happens. Okay. So here's the puzzle or project I set for myself back then, which is, can we get this picture to emerge from a quantum mechanical calculation without making any more restrictions on the quantum state other than those two mild ones I made at the beginning? And if not, what are those other restrictions that we need to make? Okay. So I'm going to assume our system is finite so that it has discrete energy eigenvalues. There's no continuum part of the spectrum. Time evolution is just governed by the Schrodinger equation, which just means the energy eigenstates change by a unitary operation, which just puts a phase factor here. And I'm showing my roots as a particle physicist by not putting in the h bar here. Particle physicists all believe h bar is 1, so we don't write it down. Okay, so now we can just formally calculate an expectation value, and by just sticking in this expansion of the actual quantum state. Oh, and I should say these C alpha coefficients of each energy eigenstate, that's what tells you what the initial state was. Okay, so we want to assume as little as possible about the properties of these C alpha coefficients. Okay, so this is just a straightforward plugging in the state, but I'm writing it as sum of two terms. There's I'll call it the diagonal term, where we have the diagonal matrix elements of A in energy eigenstates, a sum over alpha and C alpha squareds. I guess I should say the sum of C alpha squareds alone without the A's, that's just 1. That comes from normalizing the state. So this is some sort of average of these diagonal matrix elements. And then we have the off-diagonal terms where we have the time-dependent phase factors in addition. Okay, and so again, here's the picture. And again, the puzzle is how do we get this formula to reproduce this picture? So if we stare at the formula and the picture long enough, a couple of things we can realize. Let's time average the picture. So I want to take the average value over a very long time. And if we do that, the answer is the thermal average, right? Because most of the time, the actual expectation value, according to our expectations of how StatMech works, should be close to the thermal average up to small fluctuations. And occasionally there might be a rare large fluctuation, but they will be rare, so they won't contribute to the long time average. We can also take the long time average of the formula. And here it's clear that this term, which is time independent, survives the long time average unchanged. And this term will eventually go away because we'll be integrating over these phases and they will integrate to 0. However, I do want to emphasize that the length of time you need to average over to get these terms to go away is huge. These are the many body energy levels of the gas. There's a lot of them. They're very closely spaced. The spacing between two nearby levels goes like e to the minus the number of degrees of freedom. So the spacing is exponentially small. That means to get rid of this by time averaging, you need to average over an exponentially long time. So this is not a time average that corresponds to anything that happens in a laboratory. It is strictly a tool of the theorist to compare the picture to the formula. But I'm a theorist, so I can do it. Okay, so having made that observation that this term is the long time average of the formula, and this object is the long time average of the picture, we conclude that those two should be equal, at least approximately. And everything else, the fluctuations away from the long time average, including thinking of this initial thing as a fluctuation of some sort, all of that has to come from the remaining time-dependent terms. But now we have a puzzle. And the puzzle is, I just told you that these two things should be equal. But this thing, the thermal average, all it knows about the initial state is the total energy, because that's in the, I needed that to get the beta that I used to do this thermal average. This thing, on the other hand, this looks like it depends very sensitively on the initial state. I've got all these C alphas in it. The C alphas all depend on the initial state. So how could it possibly be that this thing, which looks like it depends very sensitively on the C alphas, how could it possibly end up being equal to something that doesn't depend on the C alphas? So here's a way that could happen. Suppose these diagonal matrix elements just happen to vary smoothly with the energy. I'm just pulling this out of thin air at this point. I'm just saying, what if? What if that was true? These are all numbers we could in principle compute if we really understood our quantum system and we had a really good computer. we could compute all these, and suppose we compute them one by one, and they happen to lie along a nice smooth curve like this. What if that was true? Well, then we can plot on the same axis the C alpha squareds. Those are the red lines here, the red dots. And those can jump around a lot because we don't know how, we're not trying to say anything about them, except we know that we've asked them to please not give us a too big quantum uncertainty in the energy. So these are going to cover some finite band. And now the average that we want to compute, the sum of the C alpha squareds times the A alpha alphas, we do that by multiplying red dots by blue dots and then adding them up. But because the blue dots within this range all have mostly more or less the same value, something like 4.5 on this completely arbitrary scale over here, it doesn't matter if this one is high and this one is low, or that one is high and that one is low, because after we multiplied them by the blue dots, we're still going to just end up here anyway. Okay. So, if by some miracle it turned out that in our system these A alpha alphas varied smoothly with E, then, can I go backwards? It's probably a bad idea. Then we can understand how these two things can be equal. This is the most important point in the talk. So if there's a question, ask it now. Okay. Okay, so the conclusion. If these diagonal matrix elements vary smoothly with alpha and delta E is sufficiently small, then this sum will depend only on E, because it only cares about where the center was of the energy range. And then a slightly less obvious conclusion. Once we know that it depends only on E, it has to equal the thermal average. And that's because we compute the thermal average by replacing the C alpha squareds with Boltzmann weights, with e to the minus beta E alpha. And Boltzmann weights fulfill the two conditions that the energy is extensive and the delta E is subextensive. And so Boltzmann weights are an example of a possible choice of the C alpha squareds that we would be allowed to use here. And if we use those, then we get the thermal average. But we've just concluded that this doesn't depend on exactly what the C alphas were. So in fact, this average has to, not only is it a smooth thing, but it has to be the thermal average. And that then means that each of these individual A alpha alphas is also the thermal average. And that is a phenomenon to which I gave the name eigenstate thermalization. The idea is that the energy, the expectation value of an observable in an energy eigenstate, that's what this A sub alpha alpha is, that is equal to the thermal expectation value. That is, the energy eigenstate has given us the same answer as a thermal state. Up to corrections. I guess I said that on the previous slide. Oh, what am I doing? I don't know what happened. Okay, it gives us this up to 1 over n corrections. This is where we need large N. This is like in StatMech, the difference between a microcanonical ensemble and a canonical ensemble. If you calculate those things, if you calculate some expectation value in two different ensembles, they differ by fractional corrections of 1 over n, and that's why we need large N. Another way to say what eigenstate thermalization is if you do quantum StatMech with a microcanonical ensemble, you're supposed to take a slice of states in energy, a slice of energy eigenstates. How many energy eigenstates do you need to put in that slice? The eigenstate thermalization answer is 1. You only need one energy eigenstate to put in your microcanonical slice. Each energy eigenstate constructs the microcanonical average. Okay. Okay, so again, if we had this miracle that the diagonal elements were smooth, then we get this very nice result, but it all depends on the miracle. We also, though, need to understand that not only are we getting the long time average right, we also want the actual value itself to be close to the thermal value most of the time. We don't just want the averages to agree, we want this to be close. And how can that happen? Well, this is actually a little easier. This will happen if all these off-diagonal matrix elements are small in some suitable sense. Because this is just some average. Remember, the c squareds have to sum to 1, so we're just taking some complicated average with phases of these things. And if these are all small, then most of the time this will be small, and we're done. However, at a particular time, like time 0, we can cleverly choose the c's so that all these individually small terms add up coherently and make something big. That's how we can get an initial state with a large deviation from the initial value to the thermal value. But then as time goes on, these phases will turn on. The coherent addition that we want to do in this sum will become incoherent as the different phases turn on. It won't sum up coherently anymore, and that's what produces this decay back to the thermal average. Okay. So, for that to work, yeah, there can be revivals, but the revivals occur at e to the n times. Right? I mean, revivals occur on the inverse, on the time scale that's inversely related to the level spacing. And the level spacing is exponentially small in n, so recurrence times are exponentially large in n. So if you can wait e to the Avogadro's number of years, then you can see a recurrence. And if not, well, too bad. Other question? Okay, but that's all very nice. At least I think it's very nice. But I invoke two things I pulled out of a hat. One is that the diagonal elements vary smoothly, and that the off-diagonal elements are small in some sense. So, does that make any sense? Do we know any systems where that happens? And the answer is yes. This is where the stuff in the quantum chaos literature turned out to be extremely useful. Both these facts are known to be true at various levels of rigor for quantized chaotic systems. By which I mean you start with a classical system that's chaotic throughout its phase space, and classical chaos means nearby trajectories diverge from each other exponentially fast in time. And starting in the 1970s, various people, Michael Berry is one of the main figures in this, started trying to understand the quantum mechanics of such systems, and is there anything special about the quantum mechanics? And turns out there is, and it's a beautiful subject, which I learned a lot about. Let me show you a distinction. Classically, first of all, the simplest systems that are fully chaotic are so-called billiard systems, where we just have a particle bouncing around in some shape. It can be in any number of dimensions. Of course, it's easier to look at 2 dimensions. And whether the motion is integrable or chaotic depends on the shape of the billiard. So rectangles, ellipses, circles produce nice regular motion. And the reason the motion is regular is that there's an extra conservation law in this case. Here it's just linear momentum, up to sign changes from reflections. It's just linear momentum in each direction. In the circle, it's angular momentum. In an ellipse, there's a sort of distorted angular momentum that corresponds, and so on. However, other equally simple shapes, a circle inside a square, a stadium, which is two half circles separated by line segments, a cardioid. Motion in these billiards is chaotic. Trajectories diverge exponentially. Every time you hit a wall, there's an exponential change. Well, there's an infinitesimal change, but they compound exponentially. And so you can just clearly see the difference, visually see the difference in again, this is all classical trajectories in integrable and chaotic billiards look quite different. Okay, what about quantum mechanics? So quantum mechanics in a billiard is a straightforward, in principle, straightforward problem. If you didn't care about the boundary, it's just a free particle, so we could write down a plane wave as a quantum mechanical wave function. And if the energy is fixed, that fixes the wave number of the wave vector, that is the magnitude of, oh, what did I do? I pressed the wrong button again. The magnitude of this k. However, the direction is arbitrary, and in 2 dimensions, we could point our k's in any direction we want, but we have to give them all the same magnitude so that they all have the same energy. And then we could sum up the different plane waves with the different k vectors and add them up with some coefficients, which I've called c again, although they have nothing to do with the previous c's. And then we would try to get our wave function to vanish on the boundary of the billiard, because that's the usual quantum mechanical hard wall condition that the wave function has to vanish. And so people actually compute eigenfunctions in exactly this way. They have the computer search for C's which fulfill those conditions. And Michael Berry, again, one of the towering figures of quantum chaos theory, way back in 1977, made a conjecture that these coefficients of these plane waves would look like Gaussian random numbers. Of course, they're not really random. You can compute them. But they would look like as if they were, you had a pseudo-random number generator that was drawing numbers from a Gaussian distribution. And he made this conjecture before there were computers that could actually calculate these things, but it turned out to be remarkably correct. Arne Baker has done a lot of work on actually computing these in various systems, and here are 2 figures. This is a density plot of an actual energy eigenfunction in the cardioid billiard. And this is a random superposition of plane waves with the same energy. And you're supposed to look at these and say, yeah, those look pretty much alike. Now, of course, we can also do fancier statistical tests. And these things all pass those tests. If somebody handed you an actual eigenfunction, and said, is this an eigenfunction or is this random? It's very hard to tell. Okay. And well, I mean, of course, you could compute the boundary and then see, but anyway. Okay. Oh, let me say something else about this. This eigenfunction is more or less uniformly distributed. You can see the thick lines where there's ridges where the wave function is high, but the thickness of these thick lines is controlled by h bar. And so as we go to a more and more classical limit, these get small, the width gets smaller and smaller. So what you basically see is a uniform background and then very rapid fluctuations. So if you take some observable, you compute the expectation value of some position observable, you would integrate over this, and those very rapid fluctuations would not affect your your computation, and it would look just like you had just averaged over the billiard. And similarly, oh, what am I doing? I'm going the wrong way. That's my problem. Similarly, I want to go back one more. Similarly, we're more or less uniform in momentum space because we're not, preferentially picking out k's that point in some direction. Each plane wave gets a random coefficient. Some of them are big, some of them are small, but the big ones are more or less uniformly distributed, just like the small ones. So more generally, this means that a random wave function, in a suitable sense, looks like a uniform probability distribution over a constant energy surface in phase space. And that is a classical microcanonical ensemble. So these random energy eigenfunctions, when you squint, and you squint so that you can't see the super rapid wiggles, it just looks like a uniform distribution over a constant energy surface, which is exactly what we need to get statistical mechanical results. And in fact, this is a theorem. The Schnirelmann theorem, proposed by Alexander Schnirelmann in the 60s, there's a very nice Scholarpedia article on this. Most of the literature on this is very technical. This is a good article. And it says that these diagonal matrix elements in a system that you got by quantizing a classically chaotic system, that these do indeed go over to the classical microcanonical average of A, plus some corrections. The first corrections scale like h bar to the 1/2, and provided in the classical limit that A itself doesn't depend on h bar. Oops. Okay, and that's actually both more and less than we need. The important part about the classical microcanonical average is that it's a smooth function. And not only is it a smooth function, but also the corrections order by order. There's some classical expression you can write down times each power of h bar, really h bar to the 1/2. And those are all smooth. So when you add them up, you get something smooth. And that's what I really wanted, something that was smooth here. And if this is some quantum spin, this is a number of order 1. It's not something that's going to 0 with h bar, which would create a different problem. So this is doing what we want. So the what I said at the beginning, the quantum chaos people knew stuff, namely, so far, the smoothness of the diagonal matrix elements. They knew stuff that I wanted to be true to get my story about statistical mechanics to work. Okay. The other thing we need is that the off-diagonal elements are small, and we can get this as well. In general, these energy eigenfunctions, every one is different, of course, and this number is going to therefore vary erratically as you change from one energy eigenfunction to the next. This is going to jump around. This will not be smooth, unlike the diagonal ones. One way to think about this is if we didn't have an A here, these would be orthogonal, and this would be 0. But A only involves a few degrees of freedom by assumption. And since it only involves a few degrees of freedom, it can't really change these very much. And so they will no longer be orthogonal, but the inner product will be small. Okay, and so we can make that more precise by computing the variance of A around its average in an energy eigenstate. We can insert a complete set of states. That will then lead to a sum of the off-diagonal matrix elements squared. And this variance should be a number of order 1 if this is like a spin. That's what that h bar to the 0 on the previous slide meant. It's not something that's quantum mechanically small, but it's also not huge. If this is a spin, this is a number of order 1 necessarily. Here I am summing a bunch of positive quantities, And in general, we expect there are a lot of states that contribute to this, because there are a lot of states with energy beta near energy alpha. Maybe we expect that those energies get far away, this goes to 0. But there are a lot of them where they're close. And so the number of these states is the exponential of the entropy, the thermodynamic entropy, at a mean energy between them. So the only way this sum can be of order 1 is if either all of these are very small or most of them are 0. Okay. Most of them being 0 can happen in an integrable system. That doesn't happen in a chaotic system, and so they're all very small. And so we can conclude they are really, really small. They're exponentially small. The thermodynamic entropy is extensive, so it scales like the number of particles. So this is an e to the minus n type number. Way smaller than we even needed. Okay, so these days, this is all summed up as the eigenstate thermalization hypothesis. I coined the phrase eigenstate thermalization. Somebody else added hypothesis. I thought of it as a fact, but they were right. It was Marcus Riegel who coined this. They were right because it doesn't apply to everything. It applies to a lot of systems, but definitely not to all. So the hypothesis is whether it applies to the particular system you happen to be interested in. And this is codified as an ansatz for matrix elements of observables, which I first wrote down a few years later. There's a diagonal term with a smooth function, and this is the thing that gives you the thermal average. Then there's off-diagonal terms with this e to the minus s over 2 codifying the size. These r's are pseudo-random numbers of mean 0 and variance 1. And then there's some envelope function that depends both on the total energy and on the energy difference. And for actual computations, which I am not going to show you, we should think of the energy as being extensive, but the energy difference as being of order 1. This on the scale on which this function varies as a function of the energy difference, the Fourier transform of that controls the time scale. So if we want our relaxation of thermal equilibrium to happen on a time scale of order 1, corresponding to something like a mean free time between collisions, that tells us that this function should vary with omega on the scale 1. Okay, and this function can be related to various two-point correlation functions, all of which is I'm not going to go into. Okay, so I told the story from the quantum chaos point of view, where we started with a classically chaotic system and we quantized it. But of course, we are interested in all kinds of systems that we don't get that way, in particular spin systems, all kinds of things. And there's not a lot of analytic stuff that can be done. However, now there's been a ton of numerics that's been done. And what's found empirically is that this ansatz also tends to hold in systems that people often call quantum chaotic, even if it doesn't have a classical limit like a spin system. And what has to happen if you have sufficiently strong interactions, not necessarily super strong, but just order 1 type interactions, and there are no obvious conserved quantum numbers. If there's some obvious conserved quantity, then one has to redo this, taking into account the existence of the other conserved quantity. If there is no other conserved quantity and your interactions are all at least medium strong, then the ETH ansatz tends to hold, according to numerics people do. Okay, that's basically the whole story. So I wrote a couple of papers in the 90s and started going to quantum chaos meetings. And quantum chaos people were very interested in quantum chaos. They didn't really care about statistical mechanics, and neither did anybody else. So these papers kind of languished. And then something happened in 2006, which was that some atomic physicist, David Weiss and his group at Penn State, did a super cool experiment where they took two clouds of atoms, supercooled atoms, in a laser trap with steep potentials in all but one direction and a shallow potential in the third direction. And so they were colliding back and forth like this. They called it a quantum Newton's cradle. This is the Newton's cradle impact ball thing. This is all taken from their paper in Nature in 2006. And this is what they saw. They saw the things collide and then bounce off. Or maybe they went through. They're bosons, and so that's the same thing. But what they did not see was a collision where they formed a single cloud that just sat there. Naively, you might expect they would form a single cloud that, thermalize. And they said in the paper, gee, naively, you might think they would form a single cloud. They don't. In that case, it's really easy to understand, though, because if you do a collision of two particles in one dimension, all they can do is exchange momenta or pass through each other. They can't do anything else. So you can't change the magnitude of momentum with two-body collisions. So that was completely consistent, and they understood that, and they said, well, in this case, we understand it, but still this calls into question exactly when does StatMech work and when does it not work. These guys, Marcus Riegel, Vanjo Junko, and Maxime Olshani, they started studying these questions numerically. They considered a system of hardcore bosons on an irregular lattice. N, they had 9 particles here, so N is 9, not exactly Avogadro's number, but close enough. And they put them all here, and then they let this go. And by then, they had heard of my papers, and they're able to check whether the diagonal matrix elements do what I claim they should do, and they found that they did. So here's a plot of a particular observable. This is some weird observable. It's some Fourier mode of the number density. I don't know why they liked this, but they did. And the blue line, this is versus time. It starts out of equilibrium. This solid line is three different the canonical ensemble, what they call the diagonal ensemble, which is just throwing away the time-dependent terms. This is the microcanonical ensemble. The canonical ensemble is actually a little bit off, and that's because n is only 9. Okay, so 10% effect. And then this is a bunch of different observables comparing microcanonical and 2 different eigenstates. So the x-axis here is a bunch of different observables, and we're just checking whether the eigenstate expectation values match the microcanonical, and they do for everyone. So this beautiful demonstration that for this model, this works. And as a test, they also considered straight line lattice. This version turns out to have extra quantum numbers. It's integrable. And now where you would expect everything to lie on a single line, it doesn't. I mean, if eigenstate thermalization held. And it doesn't hold in this, which is the prediction, because this has extra conserved quantities. Okay, that's basically the whole story. So, of course, as we just saw, there are lots of systems that don't obey eigenstate thermalization, integrable systems where you have extra conserved quantum numbers. And again, these guys developed the theory of this, what to do about those extra conserved quantum numbers. You have to write down a so-called generalized Gibbs ensemble. Also, there's a phenomenon of many-body localization, which can happen in particular, if you put some disorder in your system. The energy eigenfunctions, instead of spreading out, can get stuck on a defect. And those systems, even though they would obey this condition of being strongly coupled and no conserved quantities, they can not thermalize, not obey eigenstate thermalization. There's a nice review of this from about 10 years ago. And if you want to see thermalization in those systems, even though you can't choose the initial state completely at random or completely at will, there can still be large classes of initial states that thermalize. So this led to a bunch of confusion about exactly which states thermalize and don't. People are still trying to sort this out. Or, of course, in the real world, it's very hard to isolate things, so maybe something has come along and bumped your system, and that's what made it thermalize. Okay, conclusions. Eigenstate thermalization can explain how isolated quantum many-body systems thermalize. So that is the answer that I wanted when I started exploring this after getting my teaching assignment. I am satisfied with this. Whether you are or not, I can't tell, but I'm satisfied. It makes me happy. Unfortunately, I didn't figure all this stuff out until after I'd finished teaching the class. So I did not tell the class. I told them the usual stuff in the books. They seem to believe it. Okay, and one example where we, certainly at a theoretical physics level of rigor, if not full mathematician rigor, we have a class of examples that obey the eigenstate thermalization hypothesis, start with a classically chaotic system and quantize it. And this work continues to this day, with the dawn of atomic physics in the mid-2000s, where the atomic physicists can now do all sorts of interesting experiments and exploration of all kinds of systems that they can model with their cold atoms. There's now a very active field trying to understand, what is a more complete set of ideas, which categorizations apply to which systems, and so on. So happily for me, this is, there was that roughly 10-year period where no one was interested, and now a lot of people are interested, and so that's a lot more fun. Okay, and gracias.
Okay, so thank you very much for the beautiful talk, and we have maybe a few minutes for 2 or 3 questions. Yeah.
Hi, thank you for the talk. Okay, the ETH hypothesis, the way you present it, it works for the average of observables. So it doesn't really tell you that the density matrix is going from pure to mixed.
No, because
right?
the density matrix does not go from
right.
pure to mixed.
So it somehow it shows that you have thermalization, but actually you can do spin echo, Loschmi echo experiment, and you will see that it's not really thermal. So my question is, but you could look at, for instance, reduced density matrix of a part of the system and see if that particular part is actually going to the Gibson sample or whatever. So the ETH hypothesis can help you to understand how if you take a part of your system, you go to the real thermalized density matrix.
So let me say a couple of things. First of all, for things like spin echo, that's something where you have very precise control, and the spin echo occurs in an order 1 time. The sort of natural Poincaré recurrence or Heisenberg recurrence time here is exponentially large. So if you haven't carefully engineered your system to have a spin echo, that's effectively an integrable system where you have enough control. The issue of, there's another way we could think about this, which is, suppose I look at a subregion of I have a lattice system or something, and I look at a subregion, and now I take all the observables that live in that region, and I say, okay, I'm going to put all these on my list of ETH observables, and now I conclude that if I look at energy eigenstate matrix elements, those will give thermal values. if that region has, it needs to be large enough so that I can ignore area effects. There's an area volume. Okay, so I want it big enough that I can say, then if I asked you to compute a thermal average for observable that live there, you would say, well, I don't need to know everything else. I'm just going to take e to the minus beta h for the h of this subsystem. And that will give me the thermal average. And so what that says, if you, this is probably not clear from what I've said so far, but if I take an energy eigenstate, form the ket broad and make it a density matrix, trace over all the degrees of freedom outside some region, what's left will be e to the minus beta h for the smaller subsystem, up to surface volume effects. You have to worry somewhat about surface effects. But so yes, so those two pictures are equivalent in that sense.
Okay, thank you. I have a related question. If you consider, for example, that you have random matrix, and instead of performing thermal average, you perform ensemble average. Mm-hmm. Do you obtain exactly the same conclusion if I have Poissonian distribution, I don't have thermalization, if I have a Gaussian orthogonal ensemble, I have it, for example?
Yeah, so Josh Deutsch's paper that came out a few years before mine, that was his model. He imagined you had you can think of it as a free particle Hamiltonian that you've diagonalized, and then he wanted to add a small perturbation that he thought of as a random matrix, random matrix. And then when you diagonalize the complete thing, even if you put a small coefficient in front, you get diagonal elements that are uniform again. So that was his approach. So for a system that is plausibly modeled by some sort of random matrix, then yes. The issue I would say is, how do we know if our system is plausibly modeled by a random matrix? But if we believe that for whatever reason, then yes, all this can be done more straightforwardly because we can just do the ensemble averaging.
Okay. Other questions?
I've heard of classical systems which have some regions of phase space where they're chaotic and others where they're not. Are there quantum analogs or places where the ETH fails?
Most classical systems are like that. If you just wrote down some classical Hamiltonian, it would probably have regions of phase space that are chaotic and what are called islands of integrability. And of course, people have studied those quantum mechanically as well. It's very hard to do anything precisely, really convincing mathematical physics on those. But of course, there are numerical studies, and what happens is there are energy eigenfunctions that live in the chaotic regions, and other energy eigenfunctions that live on the islands, and then there are some that are mixed up in between them. And the number of energy eigenstates in the chaotic region versus the number in the integrable regions scales with the phase space volume of those regions in just the way you would expect. So if you were actually in such a system and you picked an initial state that lived in an island, you would probably be stuck in the island. Now, there tends to be diffusion processes where you can leak out of the island, and it all gets very complicated. But yes, all those things have been studied. There aren't very many particularly rigorous results, and generally it's a big mess. No real-world examples. I'm sorry? No real-world examples? Oh, real-world examples. Yeah, it's very easy to write down kicked rotor is in that category. Lots of things are in that category. And then, but the studies that are done are mostly numerical because it's very hard to come up with analytic results. But it behaves pretty much the way you would think. You can get stuck in the integrable regions. Sometimes you can tunnel out in quantum mechanics, and all these different phenomena occur, and they compete with each other in different systems.
Okay, so let me remind you again that you are invited to join us for a coffee break in Ex Biblioteca, and let's thank Mark again for the beautiful talk.
Thank you.